Hello and welcome everyone to Non-IITian. This is a problem in real analysis from ISI JRF Mathematics 2025 MTA question 1. And this problem is actually related to polynomial growth versus exponential decay. If you are enjoying the content, please don't forget to like, share and subscribe to Non-IITian. Let's quickly go to the problem statement. So the problem says the following: show that limit n tends to infinity Pn times the integral from n to infinity e to the power minus x squared dx is equal to 0 for all polynomials px in Rx. Okay, so for overall for all real polynomials. Let us quickly see the proof of it. What will be our approach? So the approach, the problem pits a polynomially growing term Pn against an integral that decays to 0. The core idea is to prove that the integral which represents the tail of a Gaussian function decays to 0 much faster than the polynomial which can grow to infinity. How do we typically do this? So firstly we find a sharp upper bound for the given integral. Okay, then we combine the terms and we analyze the final limit. The most typical way to calculate limits in these sort of scenarios is to go through the squeeze theorem, and we'll see that that is exactly what we typically will be requiring here. So finding an upper bound for the integral, let's see. So let's consider the integral I of n given by integral from n to infinity e to the power minus x square. Now we have this integral, right? N to infinity e to the power minus x square dx. So the x which acts as a variable here, this x is greater than or equal to n, right? What does this mean? This means 1 over x is less than or equal to 1 over n. Fine. So we will be using this, so it is given here that 1 over x is less than or equal to 1 over n by the argument we presented. So now e to the power minus x square can be written as 1 over x times x into e to the power minus x square. The sole reason why we did this is that so we are able to integrate this particular part using the method of substitution so as to come up with an upper bound for the integral of e to the power minus x square. So therefore for x greater than or equal to n, e to the power minus x square is less than or equal to 1 over n times x into e to the power minus x square from this particular value. So therefore if I just integrate it out, I can take the 1 over n outside. I am left with this integral. Here I can substitute x squared to be z. This is a very simple method of substitution. By solving this and taking, so this is an improper integral, so you can just evaluate this limit by taking it in the following way: limit t tends to infinity, integral n to t x times e to the power minus x squared dx. Solve the integral as you do, and after solving the integral, take t to infinity. Eventually you will see that the value will come out to be half e to the power minus n squared, capital N squared. Okay, is it clear? So therefore our integral from n to infinity, which was less than or equal to 1 over n, times the integral n to infinity x times e to the power minus x squared, this will eventually come out to be e to the power minus n squared upon 2 to the power n. So we see that this integral minus x squared, this is obviously greater than or equal to 0. This will come out to be e to the power minus n squared upon 2n. Okay. Now I choose an arbitrary polynomial pk of the px of the form ak x to the power k plus ak minus 1 x to the power k minus 1 and so on so forth till a0, and we have to find this particular limit. Now what is the value of pn from here? So pn will be just ak n to the power k and so on till a1 n plus a0. So therefore 0 is less than or equal to pn times this, which is less than or equal to pn times the integral, the value of the integral we approximated. So observe that if I am able to show that this goes to 0 as n tends to infinity, then by the squeeze theorem we are done, and that's exactly what we will do. Okay, so what do I have here? I have limit n tends to infinity ak n to the power k plus so on and so forth till a0 divided by 2 times n into e to the power n square. Now one thing which you can try and do here is directly apply the L'Hospital's rule. But typically speaking, you can just distribute this out and apply this particular result and we will be done. Because n to the power k upon e to the power n square, this goes to 0 as n tends to infinity, because the exponential growth to infinity is much faster than the growth of the functions of the form n to the power k as n tends to infinity. So this will eventually go to 0, and so if you distribute this sum out as, say, limit n tends to infinity, so this will become a naught upon 2n e to the power n square plus so on and so forth till limit n tends to infinity. I have here ak n to the power k minus 1 upon e to the power 2 times e to the power n square. So this will go to 0 as n tends to infinity, this will go to 0 as n tends to infinity. So the whole limit just evaluates to 0 as n tends to infinity. And therefore by the squeeze theorem we are done, because therefore by squeeze theorem we conclude that limit n tends to infinity Pn integral n to infinity e to the power minus x squared dx is equal to 0. And this is exactly what we require to prove. Got it? Thank you for watching. Please like, share and subscribe to Non-IITian if you like such videos. Meet you guys soon.